Welcome to part 6 of the series, where I'm building a 6502 compatible machine based on Ben Eater's SAP1 design. This is Battle Chess, running on an AppleWin emulator, and I've modified AppleWin to use the microcode that I'm going to use in this design. Interestingly, this code used the return from interrupt instruction, which I haven't implemented yet. All other instructions are from the microcode. Interestingly, when preparing this video, I found this little gem that I didn't know about before. When two knights fight each other, the winning knight first chops off an arm, then the other arm.
Victory is mine!
A leg.
I'll have your leg! Right!
And then the other leg.
And then...
I wonder where they got that idea from. Anyway, here's Ben Eater's SAP1, which is based on Albert Paul Malvino's original description, and in this series I've bulked it up a little bit. Let's have a look at the program counter and the memory system in a bit more detail. Let's start by looking at the connection between the data lines on the memory and the W bus. Now, technically, I could have connected the data lines from the memory directly up to the W bus, because both memories have tri-state data lines. If I deassert the output enable signal on both memories, then they shouldn't interfere with the W bus. But in this case, I decided to add a 74HC245 to isolate the memory data lines. The reason for doing this is in case I'm mad enough in the future to try and add a video controller. It would mean that I'd have to add extra logic to every device connected to the W bus to silence them during video transactions. And I've already wired in most of these chips, so I don't really want to do that. Adding in this 245 means that I can use the W bus and the data bus on the memory at the same time, without too much extra onerous logic. The enable signal and the direction signal on the 245 come directly from the sequencer. Let's move the W bus over to the side and connect up the static RAM and the EEPROM to this new 245 that we've added. Looking from underneath the board, the W bus and the 245 are here. The socket for the static RAM is on the left, and the socket for the EEPROM is on the right. Let's move forward in time. Most of the memory data bus is done. These red signals below are actually part of the sequencer. Next, I want to wire up the lower 8 bits of the system memory. We need 2 of these 74HC161s per 8 bits, so we need 4 overall, but I'll just concentrate on the lower 8 bits for now. If we were to connect up the outputs of these 161s directly to the memory, we'd run into a problem. That's because we want the effective address A low register to also be able to drive this bus. The 161s don't have tri-state outputs, so we could get contention between these two chips. We looked at this in the last video, and an easy way to solve it is just to put a 245 buffer between the 161s and the main memory bus. Next, we arrange it so that only one of these devices can be driving the memory at any one time. For branch instructions, we need to be able to read the value in the program counter, while some of the more complex addressing modes need to be able to read the results in the effective address A register. To facilitate this, I've added this 245 in the return path, but it also means we have to use the PC select signal to determine which of the registers we read back. The program counter needs to tap into the W bus. This new yellow bus in the middle taps into it on the left and connects to the program counter circuit on the right. The W bus connects to the upper byte circuit as well as the lower byte circuit for the program counter. These are the lower bits of the address bus, and you can see I'm wiring up the blue address bus while I'm wiring up the yellow W bus. If possible, and if I plan enough ahead, I try and wire from top to bottom or bottom to top. That saves me trying to solder in between two existing wires and potentially melting the shielding, which could cause an intermittent short at some stage later on. They're awful to try and find. Most of the lower 8 bits of the program counter are done now. The blue address lines coming out of the program counter circuit now need to be hooked up to the memories. I have this expansion port above, which is a 36-pin header, and I plan to use this for testing and for expansion later on, but I want all the address lines to go to that as well. It's a bit neater here. I'm going to have to solder to these pins between the wires here, but the blue Kynar wire wrap wire is actually a lot more tolerant to heat than the yellow wire is, so I'm less concerned about having to solder between blue wires. It's actually quite an effort to get the blue shielding to melt, but you just touch the yellow shielding and it's gone. That's the program counter for the lower 8 bits wired in. Now I have to concentrate on the upper 8 bits. It's the same circuit, well, a replica of the same circuit, but the blue output address lines go to different pins on the memory chips. Now I just need to replicate the circuit for the lower byte, which is up the top of the screen, for the upper byte, which is in the middle of the screen. Now I'm about halfway done, so I'm making pretty good progress. I should be able to get some instructions working once the program counter's finished. Now both the upper and lower byte of the program counter are complete. Good times ahead. All of the address lines are wired up to the chips and to the expansion port. Now, I didn't just randomly decide on pins for the expansion port. I use a pattern compatible with the port assignment on an Arduino Mega. This is just a temporary setup. I actually plan to use an Arduino Nano for the keyboard interface and floppy disk interface. Alright, let's power it up. Fortunately, that didn't happen. But getting it to work felt a bit more like this. That was a slightly modified version of the Ariane 5's maiden launch. We'll come back to that a bit later. The first thing I'm going to try is the famous no-op test. If every read from memory is EA in hexadecimal, then the program counter should just step smoothly through the address space. I'll hardwire the memories so that their output's not enabled. Then I'll get the Arduino, which also has access to this bus, to write the value EA. This is where I set EA, and I also assert reset for 10 clock cycles. The output of the instruction register is highlighted here, and we can see it contains the value 0A. Not exactly the value I was hoping for. I also noticed that the step counter didn't start at 24, which is the reset program, and it shouldn't matter which instructions selected. I poked around a bit, but then I finally decided to check whether the Arduino was actually writing EA to the W bus. I need to remove this set of LEDs, which are the upper 8 bits of the address bus. 1, 1, 1, 0, 1, 0, 1, 0. Well, that's EA. After some poking around, I found that the output enable signal on this latch didn't have a signal on it. Then, sure enough, when I looked underneath, there's nothing connected to it. The output pins from this latch are connected to the output enable on a whole bunch of other latches attached to the W bus, so who knows what sort of havoc this could cause. Alright, that's been fixed. Now let's have another crack at it. We seem to be in the reset sequence here. Waiting. And there we have it. EA. Now let's have a look at what the address bus on the memory is doing. Hopefully it should be counting up in binary. The address lines on the memory are represented by these green LEDs, and unfortunately the way I program the microcontroller, the lines are flipping between the program counter and the effective address A registers. I edited the video to show only the program counter frames, and here we can clearly see it counting up. I ran into some other problems though. First, the machine didn't always reset properly. Here's a case where it didn't go through the reset sequence, and when it did, the reset vectors were wrong. It turns out I wasn't asserting reset long enough. If I happened to randomly start in an instruction that took more than 10 cycles, The reset signal might be deasserted before the next load. The maximum possible instruction length is 24, so I changed it to 26 just to be sure. The problem now, though, is it could execute a couple of instructions during reset. I wasn't super happy with this solution, but then I remembered Steve Bradbury's gold medal win. Here he is at the back of the pack. And quite honestly, that's not bad for someone from Australia, given that most of the country is a desert. Pretty, you just got to get over the line. And I can always fix it up a bit later anyway. The problem now is I'm not getting the correct reset vectors. This is the constant register, and when I go through the reset sequence, its output is never being enabled. After some more digging around, I found out that I'd accidentally crossed some output enable signals with some clock signals to at least a couple of the registers. Annoying but easy to fix. The 6502 has a reset vector starting in FFFC. This is hard-coded into the microcode. Remember that our constants are 4 bits sign extended to 8 bits, so this is where the FFFC comes from. Now when we reset the machine, we can see the FFFC reset vector being sent to the memory. That's pretty good, I'll take that. I've loaded the ROM with the code from Apple Win, and let's see what the machine should do after reset. It should load this reset vector, FA62, into the program counter. At this location, we see the instruction D8, which is a clear D. The program counter should be incremented by 1 and point to the next location. At FA63, we find the JSR instruction, so the program counter should jump to location FE84. There we find load Y immediate with 0FF hexadecimal. The program counter should be incremented by 2, where we should see a store Y at 0 page location 32. The program counter should increment by 2 again. We should see this return from subroutine instruction. After the reset vectors, we see the program counter pointing to FA62, and we see the value D8 in the instruction register. Well, that's looking good. Next, we're at location FA63, and we see 20 in the instruction register, which is JSR. If you'll remember from a couple of videos back, JSR has 15 micro instructions. You can see the blue step LEDs in the middle counting up sequentially in binary. We finally get to the next instruction, and it's at location FE84. The opcode is A0, which is the LDY immediate instruction. The program counter is incremented by 2, and we go to FE86. This contains the opcode 84, which is STY 0 page. The program counter is incremented by 2 again to FE88, where we see the 60 opcode, which is returned from subroutine. Now this is going to fail because the return location wasn't stored properly, and this happened for 2 reasons. First, I haven't enabled the static RAM, which would store the stack. And secondly, we need the ALU to decrement the stack pointer in the JSR instruction. It did, however, perform exactly as we were expecting it to. Now we've gone over the W bus, the register bank, the sequencer controller, the program counter, and in the next 2 or 3 videos we'll go over the ALU, and then we should be done for now. Don't forget that I'm planning a different series to go over the microcode. Anyway, like, share and subscribe, and don't forget to press the notification bell.